Welcome to this new module. In this lesson, we will dive into the computational layer, the core of our interactive ecosystem. Its main job is to perform calculation and generate the outputs of our system. In the field of interactive arts, many tools have emerged over the years. In this lesson, we will get our hands on one of the most powerful. Its name is vvvv Gamma. vvvv Gamma is a visual live programming environment for the .NET ecosystem. It is a hybrid visual textual language designed to create complex systems in a fluid, immediate, and collaborative way. It is used for interactive installations, audiovisual performances, rapid prototyping, and large-scale multimedia application. Behind the scenes operate VL. It is a language that automatically converts what you do visually into C# code, allowing you to intuitively use advanced programming concepts like loops, objects, and conditions. To truly understand the immense potential of this tool, please pause this video now and take a look at the official vvvv showreel. Currently, 4v Gamma is natively available only for Windows, but in the future it might be available for macOS as well. For now, to run it on a Mac, you will need to install a virtual machine. In the study materials for this course, you will find a step-by-step guide to installing vvvv Gamma on both operating systems. Look for the file named vvvv setup. Once you launch vvvv Gamma, you will see a minimal screen almost entirely free of text and buttons. Don't panic. 4v Gamma hides its menus to give you a clean, open workspace. In the top left corner is the quad menu used for global software controls. Next to it is the document menu, which offers specific functions for each individual project. Let's look at some essential shortcuts. Press F1 to open the help browser. This is a highly useful resource packed with ready-to-explore examples. Press Ctrl F1 to open the general settings. Press Ctrl I to open the inspector. When you select a node, the inspector reveals all its internal properties, including hidden pins. Finally, press Ctrl F2 for the debug window. This is crucial for viewing errors and analyzing how your patch is behaving. By double-clicking the left mouse button in an empty area of the patch, we access your best friend, the node browser. From here, we will search for and create nodes, navigating by categories and packages. 4v comes with many pre-installed nodes, but you can also add packages created by the community. Just select the desired package in the node browser to add the dependency and starting use node for that specific package. Throughout these lessons, I will frequently refer to the patches included in your study materials. I highly recommend opening and exploring them alongside me while you watch the videos. Please go ahead and open the project named Fundamentals. In this patch, let's start with the basics, the IOBoxes. These are interface nodes used to display input or inspect data in real time. Right-click and drag to adjust a value or double-click to type it directly. Hold the Shift key while dragging for precise adjustments. By right-clicking the label and selecting Configure, you can even turn an IOBox into a slider and set appropriate minimum and maximum values. When working with nodes and data types in 4v, you will often need to convert data formats. In the example patch provided in the materials, I show some of the most common use cases for data type conversion. If you have programming experience, you already know the concept of a list or an array, a container that holds multiple values of the same data type. In VL, these containers are called collections. There are several types like dictionaries or sequences. However, the only collection we really need to focus on right now is the spread, which is the most common and versatile implementation in 4v. We finally arrive at the heart of visual programming, nodes. In vvvv, you must pay close attention to the data type required by the nodes you want to connect. Hover your mouse over a node's input and output, which are called pins. This allows you to see the pin name and its required data type in the tooltip. After selecting a node, press Ctrl-I to access the inspector. This provides a much more precise configuration of the node and its pins. Let's combine these concepts with some simple math. We have nodes for addition, subtraction, multiplication, and division. We also have the modulo node to get the remainder of a division and nodes to round values up or down. There are comparison nodes that return a Boolean value meaning true or false. We also have nodes to check if a number is even or odd, or to generate random values. In 4v gamma, incompatible nodes or actions generate errors, which are indicated by a red color. First of all, if you see a red outline or link in your patch, always check the tooltips. They will give you a hint on what might be wrong. Are you missing a package reference? The tooltip will tell you which one to enable. It is the wrong data type. It will remind you that, for example, a math node cannot be used with a text string. Finally, let's look at paths. They function like variables in other programming environments. They store data and make it available in the next iteration. By default, they are gray, meaning the data type is undefined. Once a path knows what data type to hold, it turns dark gray. You can also specify the data type manually via the Configure menu. A crucial thing to remember, everything entering and exiting a path will have a 1-frame delay, as the value is returned in the next frame. Keep this in mind when working with real-time inputs. Welcome to the second lesson. Here we will explore real-time 2D graphics. The core 2D library in vvvv gamma is vl.skia. It is based on Skia, an open-source high-performance rendering engine used worldwide. The final composition is drawn using a render node, which accepts an input layer containing all the 2D content you want to display. Please remember, when starting a new patch, you must always reference the vl.skia package to see all of its nodes in the node browser. Please open the patch in your course materials called 2D Graphics. Here we can observe that a Skia render pipeline consists of a few key sections. First, the paint node. It defines how a shape is drawn, such as its color or stroke. Second, the 2D primitives. They define the shape itself. Third, the 2D transformation. It moves, scales, or rotates the shape in 2D space. Keep in mind that the vertical coordinate system goes from -1.0 at the top to 1.0 at the bottom, while the horizontal range depends on the renderer window's aspect ratio. Fourth, we have the group node. It combines multiple layers and defines the drawing order. The inputs on the right are drawn on top of the others. You can easily add more inputs to a group node by pressing Ctrl+. Finally, the renderer. This is our output window. It features a convenient input pin for the background color. Press F2 while the renderer window is focused to display the performance meter. Thanks to the Set Blend Mode node, we can choose exactly how our layers blend together, selecting from a wide range of options like Screen, Overlay, Darken, or Lighten. Use the blend mode between the paint and the primitive to define how a layer will mix with the previously drawn one. You can check out all the available blend modes in the drop-down menu of the enum input. Skia works in the background with data types called SkiImage and SkiPictures to handle images and SVGs. You can load and render them using the Draw Image and Draw Picture nodes. Instead of normal renderer, we can also use the off-screen renderer. This node draws the composition in the background without opening a new window, making it accessible as an scheme image data type. Finally, using the Image Writer node, you can save the output of an off-screen renderer directly to your hard drive in various image formats. Just make sure the folder path exists and remember to specify a file name. The text node is one of Skia's 2D primitives and is used to display text. Use the Font and Paragraph Paint node to format it. With the Break at Rect node, you can easily include automatic line breaks within a defined rectangle. Use the toString node to convert a numeric value into a text string. Its format pin allows you to specify the exact number of decimal digits to show on screen. Finally, the setWindowState and setWindowMode nodes allow us to fully configure our rendering window. For example, you can customize the title bar, hide borders, or go full screen, tailoring the output exactly to your installation's needs. Welcome to the third lesson dedicated to 3D graphics. In 4V Gamma, the heart of 3D is vl.stride. It is a powerful real-time rendering engine based on Stride, formerly known as Xenco, which is an open-source game engine written entirely in .NET. If Skia handles the 2D world, like text and interfaces, Stride is completely in charge of the third dimension, lighting and complex materials. For this lesson, we will refer to the patch found in your course materials, named 3D Graphics. Let's see what's inside. A Stride render pipeline is an entity-based system. First, we have 3D primitives, which are our basic shapes. Unlike Skia, in Stride, transformation values like scale, rotation, and translation are set directly inside the primitive itself. Next, we have materials. They define the object's appearance and how it reacts to light, simulating surfaces like metal, wood, or plastic. The group node simply combines entities. In this case, the input order doesn't matter. Lights are essential. Try experimenting with different ones to see how they affect your scene. Finally, rendering. Our scene window and root scene. A few handy shortcuts when the window is focused. Press F2 for the performance meter, F4 to show the axis, grid, and helpers, and hold R to reset the camera. Let's talk about cameras. If you don't connect a camera to the scene window, vvvv uses a default one. But if you want to control the view directly from your patch, use the Orbit camera. Make sure to connect it to both the scene window and the root scene. This way, the helper tools will also be visible in the debug mode. One important detail: changes to the camera pins only take effect after a reset. You can trigger this by sending a bang to the reset pin or by holding the R key for half a second. At the end of our render pipeline, we can apply visual effects to enhance the final scene. These are called post effects. In this example, we are enriching the composition by adding a fog effect, a sharp outline, and a cinematic touch using film grain. Just like we saw with Skia, Stride also offers its own nodes to manage and configure the rendering window, giving you full control over the visual output of your application. Let's wrap up with textures. Besides loading images or video streams, Stride offers a wide range of texture sources, both static and animated. All of them can be modified in real time. You will find them in the node browser under the Stride Textures Source category. But please, pay attention. To use these sources and texture effects, you must first reference the vl.stride.textureeffects package. Once enabled, you can use a massive variety of real-time shaders to manipulate textures and mixer nodes to combine multiple layers together. Please take some time to explore the page provided in the study materials to dive deeper into the world of stride in vvvv Gamma. Welcome to the final lesson of this module, Reactive Graphics. So far we have drawn static shapes. Now we will explore the principles of animation, control and transformation applied to the real-time computer graphics. The goal is to create dynamic reactive graphics that respond to external inputs, time cycles, or specific events. In 4V Gamma, every single parameter of a node can be animated. We will see how to use essential tools like oscillators, time cycles, and triggers to animate position, scale, rotation, and color. Let's start exploring by opening the patch you find in the course materials called Reactive Graphics, Controlling Patches. Here, let's meet the engine of time, the LFO node. This node generates a continuous value that goes from 0.0 to 1.0 over a given time interval. It can be paused or reset. With every new cycle, the LFO outputs a signal that we call a bang. Next is S plus H, which stands for sample and hold. It holds the value coming into the left pin for as long as the right Boolean pin remains true. Finally, let's look at the if region. It allows you to execute parts of your patch only when a specific condition is met. It is highly efficient. If the condition is false, the nodes inside the region are completely ignored, saving precious computational power. With a switch node, we can control the signal flow in our patch. The index pin specifies which input will be sent to the output. You can increase or decrease the number of inputs by pressing the Control key and the plus or minus keys. The switch is very often used with counter nodes. A counter simply increments or decrements a value. There are also specific nodes to count within limits. Counter ranges mirrors the value when it hits the maximum, counter wrap restarts from the minimum, and counter clamp forces the value to never exceed the established limits. Now let's move to the second patch found in your study materials named Reactive Graphics Animations Triggers. Inside, we can see that LFO is frequently combined with other nodes to generate common mathematical waveforms from signal like sine, cosine, triangle, sawtooth, and rectangle waves. But what if we want to smoothly animate a value towards a new target? We use the damper. This node performs a smooth transition over a given time. Keep in mind it is not adaptive, so you must select the correct damper for your specific data type. On the other hand, if you are looking for an organic random floating movement in 2D or 3D, the Wanderer is a highly flexible node with many settings to explore. While the LFO outputs a regular repeating signal, the trigger node repeats a signal within a specified time interval, making it great for generating random bangs. The changed node, instead, sets its output to true only when its input values changes. This is perfect for tracking mouse movement. A monoflop sets the output to true for an exact specified amount of time after receiving a bang. And if you need to quickly swap two values, you can use the swap node. Finally, when working with physical inputs like a button or a touch sensor, you need the TogEdge node. It detects the exact moment the Boolean input changes from 0 to 1 or vice versa, outputting a bang exactly when the change occurs. Perfect for tracking mouse movement. A monoflop sets the output to true for an exact specified amount of time after receiving a bang. And if you need to quickly swap two values, you can use the swap node. Finally, when working with physical inputs like a button or a touch sensor, you need the TogEdge node. It detects the exact moment the Boolean input changes from 0 to 1 or vice versa, outputting a bang exactly when the change occurs.